Hello and welcome to Cashmatics. This is part 2 in my series of videos on complex numbers. Now in the first part we looked at what a complex number is, how to add and subtract them, how to multiply and divide them, and how to make the denominator of a fraction real if it's complex. Now in this video we're going to be looking at how to solve cubic and quartic equations which may have complex roots. Now in order to do this you will need to know how to divide a polynomial by a factor and also understand the factor theorem. So if you're a little bit rusty on that, or if you just don't know how to do it, go and watch my video on the factor theorem and polynomial division, and then come back to this one and then continue. And if you are ready for it, grab some paper and let's get started. Now before we start solving the equations, we need to understand something about the combination of the roots. Now we're going to do this by looking at some graphs. The list does look quite daunting there, but there's only one thing you need to take away from it, which I'll tell you at the end of this section. So let's just have a look at what these graphs tell us. So the first one pair of real and distinct roots. So this is for a quadratic, and that'll happen where the quadratic crosses the x-axis twice. Okay, so you can see you've got two distinct and real roots. The second is where you have a pair of real and equal roots, and that's going to happen where the quadratic comes down, it just touches the axes and goes back up. So you've got a pair of real but equal roots. The third is when the quadratic will completely miss the x-axis, it'll go back up without touching it, and that's when you have a pair of complex roots, and they come in conjugate pairs, and I'll explain why that happens a little bit later on. When it comes to cubics, you might have three real and distinct roots, so like that. So you've got 1, 2, 3 distinct roots. You might have three equal roots, and that's when the cubic does something like that. Okay, so it just goes through once, and all three roots happen to be the same. You might have one pair of real and equal roots, and the other one is just another real root. So you might have something like that. Okay, so that's a repeated root there. So they're real and equal, and then there's another root. Or you might have something like this. Okay, so you've got one real root here, but then with this one here, you've got a complex conjugate pair of roots, okay, because it doesn't touch the axes. Now the number of roots for any polynomial is the same as the highest power of that polynomial. So for a cubic, you are going to get three roots. And that means if you've only got one real root, the other two must be complex. Now when it comes to a quartic, you might have four real and distinct roots. So it might go something like this, 1, 2, 3, 4. Okay, so we've got 1, 2, 3, 4. Okay, so they're real and distinct. Let's get rid of that. Okay, you might also have four real and equal roots. I haven't got that on the list. Okay, so something like that. Okay, it's not the best sketch, but you understand what I mean. Okay, one pair of real and equal and two real and distinct roots. So that means something like this. Okay, so these are real and equal, and these are real and distinct. Okay, you might have a pair of real and equal roots. So two pairs of real and equal roots. So you've got one pair over here and one pair over here. You might have two real and distinct and one pair of complex conjugate pairs. Okay, so real and distinct, so something like that. Okay, so these are your real and distinct roots. Remember, there has to be two other roots, and there'll be a complex conjugate pair. You might have two real roots and one pair of complex conjugate roots. Okay, so you might have two real ones like this and one pair of complex conjugate ones. So there's your two real ones, and your other ones are going to be your complex conjugate ones. Or you might have two pairs of complex conjugate roots. So you might have something like this, okay, where you've got two pairs of complex conjugate roots because it doesn't touch the axis at all. Now the reason why the complex roots come in conjugate pairs can be explained by using the quadratic formula. So let's just say we've got x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Now for this to be complex, this bit here, the discriminant, so b squared minus 4ac needs to be negative. So let's just change that for minus 16. Let's just change this minus b to minus 4, and let's just change the 2a to 2. Okay. Now, what will happen here is you'll get minus 4 plus and minus 4i over 2, which gives me minus 2 plus and minus 2i. Okay, and this is a complex conjugate pair. So you've got minus 2 plus 2i and minus 2 take away 2i. And remember, if you've forgotten what a complex conjugate pair is, if z is equal to a plus bi, then the conjugate would be a minus bi. So it would be the complex bit, well, sorry, the imaginary bit with the opposite sign. Before we solve any cubics or any quartics, we'll remind ourselves of the factor theorem. And what it says is, if z equals a is the root of f of z equals 0, then z minus a is a factor of f of z. And if you've forgotten about the factor theorem, please go and watch my video on the factor theorem. But anyway, let's do an example. So here we've got a question. It says, given that z equals 2 is a root of z cubed minus 6z squared plus 21z minus 26 equals 0, solve the equation. So what we're going to try and do is solve that equation completely. Now this bit here, if I apply the factor theorem, that means that z minus 2 is a factor. Okay, so the first thing I'm going to do is actually divide this cubic by this factor here to get what the other factors are. So let's just write it down over here. So you've got z cubed take away 6z squared plus 21z take away 26 equals 0. Not equals 0, we don't need that bit. Okay, and let's just divide by z minus 2. So let's see how many z's going to z cubed, that is z squared, multiply it by z minus 2, so that'll give me z cubed minus 2z squared. Subtract that to give me minus 4z squared and bring down this term here. How many z's are there in minus 4z squared? There's minus 4z of them. Okay, so that gives me minus 4z squared plus 8z. Subtract these to give me 13z. And then bring this down. And how many z's are there in 13z? There's 13 of them. And then multiply that, and I get 13z minus 26, and that gives me a remainder of 0, which means this equation here can be written as z minus 2 z squared minus 4z plus 13 equals 0. Okay, so hopefully you can see why one of the solutions is z equals 2, but from here I need to get my other solutions. Now I can see straight away that I can't factorize this. There's no factors of 13 which will give me a minus 4. So what I do, I just go straight for the quadratic formula. So I go z equals 4 plus or minus the square root of minus 4 squared, which is 16, take away 4ac, that'll be minus 52 over 2, and let's just simplify that. And that gives me 4 plus and minus the square root of minus 36 over 2, which is 4 plus and minus 6i over 2, which is going to be 2 plus and minus 3i. So overall, my solutions are, now I know this is a little bit untidy, I've got z equals 2 plus 3i, and z equals 2 take away 3i. So as you can see, the complex roots are a complex conjugate pair. Now this next example is a little bit tricky. Instead of being given a real root, what you've given is a complex root. But because we're given a complex root, we can say straight away that the other complex root, or the other complex solution, would be z equals minus 4 take away I. So just by being given this, we've already got one of the other roots. So all we really need to work out is what the linear factor is. Because remember, with a cubic, if you've got two, let's just draw it for you here. Oops, no, that's not right. Like that. Okay, if you've got one real one, you'll have two complex ones. So that's the scenario we've got in front of us. Okay, so this one here. Let's just get rid of that. So what we can do is use the factor theorem, which means one of the factors is z take away minus 4 plus I. Okay, so that's the first bit of information we're given. And the other one is, the other factor is z take away minus 4 take away I. Now there's a lot going on here, and you've got to be super careful. But by multiplying these together, what we're going to end up with is our quadratic factor. Then all we need to do then is work out the linear factor. So let's just really carefully multiply all of this out. So z times z gives me z squared. And then I've got z multiplied by this term over here. So minus brackets minus 4 minus I. So that would be minus z minus 4 minus I. Then I've got minus this term multiplied by z. And then I've got plus this term over here multiplied by this term over here. Okay, so minus 4 add I and minus 4 take away I. Okay, so be really careful with this because you can easily muddle up the signs, especially with the complex numbers. So what we've got over here is z squared, take away, sorry, plus 4z, I nearly made a mistake myself, add zi, plus 4z again, take away zi. This here, this is going to give me the sum of two squares, so that'll give me plus 16 and plus 1. Okay, so what we've got is some terms that cancel each other out, so that'll cancel that one out, and what we're left with is z squared plus 8z plus 17. So all we need to do now is find out what the linear factor is, and we can do that. We can actually do that quite easily. What we know is that z squared plus 8z plus 17 multiplied by some linear factor is equal to z cubed plus 4z squared minus 15z take away 68. Okay, so I'm just going to write this in a different color. I know this is going to be something like az plus b. Okay, so that's my linear factor. So all I've got to think about is where does my z cubed term come from? There's only one place it can come from, is by multiplying this term by this term. No other term will give me a z cubed term, which means this has to be z. Okay, so this has got to be z. Now, where does the minus 68 come from? The minus 68 comes from multiplying the constants together, and those are the only two constants that get multiplied together. Okay, nothing else will give us just a number. So that there, this number at the end has to be, let's get rid of this, has to be minus 4. Okay, in fact, let's put that in orange. It has to be minus 4. All I'm going to do now is just check that these other coefficients are correct. So let's just have a look at the z squareds. Now, where do the z squared terms come from? You get 1 from there, that's minus 4z squared. That's 8z squared, and that makes 4z squared, so that's okay. And let's just check the z terms. The z terms come from multiplying these two together, so that's minus 32z. That's plus 17z, which gives me minus 15z. So that there is the other factor. So what we can say then is that's fully factorized. I can't factorize that anymore. The solutions are z equals minus 4 plus I, z equals minus 4 take away I, so that's our conjugate pair which we established right at the start, and the last one is z equals 4. And one last example, z to the power 4 take away 12z cubed plus 31z squared plus 108z take away 360. Given that z squared minus 9 is a factor, solve f of z equals 0. Okay, so what we need to do first is some polynomial division, so let's just set this up. So we've got z to the power 4 take away 12z cubed plus 31z squared plus 108z take away 360, all divided by z squared minus 9. Right, okay, now I've got to be really careful here, and you'll hopefully see why in a bit. So, first of all, how many z squareds go into z to the power 4, or what do you multiply z squared by to make z to the power 4, and that would be z squared. Now, what you've got to remember is, in this quadratic here, there's a factor missing. There's a term missing, the z term is missing, but I need to include it when I write down z squared multiplied by all of this. So let's just do that. Z squared times z squared is z to the power 4. Z squared times 0z would be plus 0z, and z squared times minus 9 is minus 9z squared. Okay, so this 0z needs to be included. If I subtract these, I'll get minus 12z cubed plus 40z squared, and let's bring this down, plus 108z. Z squared multiplied by minus 12z gives me that. Okay, and then multiply the minus 12z by all of this. So minus 12z multiplied by z squared is minus 12z cubed plus 0z squared. Sorry, 0z, sorry. So it's 0z squared, sorry. And then plus 108z. Okay, let's subtract these, and I end up with 40z squared plus 0z, take away 360, and then what have I got? I've got z squared multiplied by 40 to make 40z squared, so add 40 and multiply 40 by all of this, so that gives me 40z squared plus 0z, take away 360, and the remainder there is 0. So what I can say is f of z is equal to z squared minus 9 multiplied by z squared, take away 12z plus 40. Now this bit here is the difference of two squares, so z squared plus 3, z plus 3 and z minus 3, and this would be z squared minus 12z plus 40. Okay, so we can get two solutions from here. Let's just have a look at this. Now, just going by the fact that we're doing complex numbers, I'm guessing we're not going to be able to factorize this, and we can't. So I'm going to go straight for the formula. So z would equal minus b plus and minus the square root of b squared, take away 4ac all over 2a. So what's this going to give me? It's going to give me 12 plus or minus the square root of 16, sorry, minus 16. Change that. All over 2, which would be 12 plus or minus 4i over 2. Okay, now we'll simplify this in a bit. So what we've got as our final answer is z equals minus 3, z equals 3, z equals, now if I simplify this, I'll get 6 plus 2i, and z equals 6, take away 2i. So that's all there is to it. Well, I say that's all there is to it. It is a little bit tricky. You do need to get a lot of practice in this. I think the main problem is going to be the polynomial division first of all, and then when you're multiplying out complex factors, that can be a little bit tricky as well. But you know, watch your signs, practice it, and sooner or later you'll be quite proficient. So I hope that's helped. In the next video we'll continue with the complex numbers. We'll start looking at Argand diagrams, which is another way to express, well, to show complex numbers, and then how we can express complex numbers using what's called the modulus and argument form and what that entails. But for now, that's it, so goodbye.